Hello everyone, we're going to go ahead and get started with stoichiometric conversions. Now, with stoichiometric conversions, yes, I know that's a lot of wording and a very long and confusing word, but the idea we're looking at is how we start with one substance and use the balanced equation to move to another. This is making our prediction, so let's jump into it. Now, the first type of conversion that we look at is mole to mole. And we start with this because it's easy. This is usually going to be our one-step problem, okay? Now, in that one step, we have to have two very important things, something given to us and a balanced equation. Well, balanced equation, why is it so important? Well, it tells us how things are going to interact and the ratios we need. So it stands in as what we call a mole ratio. Now, when we write the actual thing called the mole ratio in our calculations, it's going to look a little different. But one thing I want you to note, all stoichiometric conversions, we have to have a mole ratio. So this is going to be different than what we saw with the regular mole gram because of the fact that we have two different substances to work from here. Now, when we have our mole ratio, we're usually going to have our moles of new substance on the top, the one that we're converting it to, and the moles of our old substance, the one we're getting rid of, on the bottom. Usually you'll see me write something along the lines of mole ratio equals moles you want over moles you have. Now, this helps us to remember how we're going to arrange it and which substances to go where. The old substance we need to get rid of, the new one we're going to keep on board. Now, this is sort of an idea of how it all works together. Start off in grams. We should know by now how to do each of these conversions. So, we have our grams. We need to convert them into moles of the other substance. And notice it goes to the bottom. And then we have our moles of our new substance, our mole ratio, here in the center. And then we convert out to grams or liters or whatever the case may be. Since we're dealing with reactions that sometimes produce gases and so forth, we need to be mindful of the process. Every single time, we always have to go through moles and then out. This usually means that we'll have, say, it could be 1, 2, 3, or 4 steps that we're involved in here. But all of them always have to go through that mole ratio. Now, let's look at the example we're given above. We have 2 moles of aluminum oxide are going to produce 4 moles of aluminum and 3 moles of oxygen. This sort of helps us out with an understanding of what's going on, because if I'm looking at this reaction, for every 2 moles of aluminum oxide that I use, I'm going to produce 3 moles of oxygen. If I'm doing a comparison between these two, I can set it up in one of these two ways for a conversion factor. If I'm starting off with oxygen and working my way backwards, I will have 2 moles aluminum oxide over oxygen, or if I'm starting with aluminum oxide, I would just flip it. Notice that the values that I have here on the ends came from my balanced equation. Whenever I'm dealing with my mole ratio, the numbers always come from the balanced equation. We want to keep that very, very clear. Now, let's look at it in terms of an example. The question that we're provided with says, how many moles of O2 are produced when 3.34 moles of aluminum oxide decompose? Balanced equation is there in front of us. And notice we have our given. So everything is still set up the way that we've been working from it before. Now, all I need to do is multiply the values on the top and divide by the bottom. So I'm going to take my 3.34 times 3, because 3 is above the line, and divide by what's below it, divide by 2. And I came out with a final answer of 5.01 moles of O2. So if I started off with this many moles of aluminum oxide, in the end, I'm predicting that I should make at least 5.01 moles of O2. Now, you may be saying in your head, Baldwin, why do you say I should make at least? Well, we know that we don't work in a perfect world. And so sometimes we may not have the reaction go all the way to completion, or we may lose some of the oxygen. And so what we're going to look at later is this thing called percent yield and see what happens and why things fall short. Let's go ahead and keep looking at examples. So, another example that's given to us. We'll work through the first one. Different equation. Let's write it out. So we're given 3.84 moles of C2H2 or ethene, and we're trying to figure out how much O2 is needed. So notice that it doesn't just have to be on the opposite sides of the arrow. It can be comparing two things on the same side of the arrow. I could look at it and say, if I produced so many moles of CO2, how many moles of water did I produce? All of that still works because of the fact that we use these mole ratios. Well, let's go ahead and take a look at it. So 3.84 is my given moles C2H2. I'm going to make my table. Now, according to my example, since I have moles of C2H2 here, that has to go down, and I'm supposed to put in 2 moles of C2H2. And how many moles of oxygen do I also have to put in? Well, looking at my equation, it says 5. So 5 moles O2. So, do I have what I was looking for? Yes. It said how many moles O2. So O2 is at the top, and this one cancels. Plug it into your calculator. 3.84 times 5 divided by 2. And I came out with 9.6 moles of O2. Let's look at one more example, and then the last one I'm going to leave for you. It says how many moles C2H2, so I'm looking for moles of C2H2, are needed to produce 8.95 moles of H2O. So 8.95 moles H2O. I'm going to go ahead and make my conversion factor. Well, since I'm starting with moles H2O, 2 moles H2O goes to the bottom. And for my C2H2, I have 2 moles. Now, some of you in your head might be thinking, hey Baldwin, you notice that it's 2 moles over 2 moles, right? So that means we're going to get rid of this unit, and we should end up with what? 8.95 moles of C2H2. Because of the fact that we have a 2-to-2 relationship, it's really goes to a 1-to-1, and we come out with the same value. Now, this last problem, I left that one just for you. Go ahead, take a moment, look at it, and then we'll go on from there in the next video. Have a lovely day.